Hello, my name is Keith Cochran, and I, along with Dr. Peter Hastings of DePaul University, have collaborated with Clayton Cohn, Nicole Hutchins, and Dr. Gautam Biswas from Vanderbilt University to perform this research. Our paper is numbered 242 and is entitled Improving Automated Evaluation of Formative Assessments with Text Data Augmentation. In this talk, I will first describe the problem we are attempting to solve, then provide some background on prior research in this area, and next I'll explain the methods that we performed, then show the results and discuss them, and I'll finish up with conclusions and areas of future research, and finally I'll open the floor for questions. Our research is focused on helping teachers and students with natural language responses to STEM-based topics. One method that has previously been employed with success are formative assessments. These help students learn components of knowledge used to then solve larger problems. It also helps the student improve ways to communicate conceptual understanding of the target domain with others. Teachers become more aware of areas of difficulty, and formative assessments can help students develop their conceptual understanding of the domain while supporting their self-assessment skills as well as their self-regulated learning skills. The difficulty is that formative assessments take time. Teachers need to evaluate short answer and essay responses to determine what feedback to provide to the student. This may result in a few days' delay in feedback on the student responses. The sooner the feedback can be delivered, the more opportunity that the feedback can be received while the brain is still in a more receptive state. We need immediate feedback to support learning in a more optimal way. When the information is fresh in the student's mind, they are thinking about the feedback as they improve their answer, therefore improving learning. Feedback should also be as fast as possible. So can a system aid teachers with formative assessments to allow for immediate feedback and adjustments tuned to individual or groups of students? Natural language processing has used recurrent neural networks in the past to try to understand the semantic intent or causal reasoning in student responses. However, these RNN systems must be trained from scratch. For a domain that suffers from small data quantities, this is quite limiting. The BERT architecture is a transformer model that has been pre-trained on large quantities of data, including the book corpus and Wikipedia. Other BERT models include other large datasets as well. With these BERT models, state-of-the-art performance has been achieved on many tasks in the realm of natural language processing and has been greatly enhanced by their discovery. AI models typically need millions of data points to perform well. Deep learning models like BERT especially need data to perform well, and data scarcity is prevalent. In many practical education contexts, with student short answer or essay studies, relatively few student responses are available, maybe 100 or less samples per question, and many NLP approaches require much more data. Image processing leverages the use of augmented data when data is scarce. It's easy to take an original image, then scale, flip, and rotate the image to provide more data. It's more difficult to do this with student responses, and it is one of the problems we are addressing in this work. So how do you augment sentence data? One common text augmentation technique is back translation. Here, we take a sentence written in English, and this example is actually a student response from our data in this experiment, and next we translate that into German or another language, and then back to English again. This leverages the power of language translation, which is a feature of BERT. One drawback is that there is no guarantee that the final sentence is semantically similar to the original sentence. What comes out of the translation could mean something completely different. Using this augmentation method could potentially train the model with incorrectly labeled responses. We chose not to use this method in our experiment. There are less aggressive methods for augmentation that have a smaller probability of semantic variance. Masking is one of those techniques. This is where a word is removed from the original sentence and replaced with the word mask in brackets. The BERT model will then substitute the masked word using a parameterizable number of words that have the highest probability of completing the sentence. Noise is a technique that alters a word in a sentence by inserting, deleting, or changing one character in the word. Hyponyms, which are words that are more specific, are used as substitutes as well. In this example, the word sizes can be replaced by areas, showing a more specific measurement of size. Hypernyms, which are words that have a broader meaning than the original word, can also be used. So the term magnitude is replaced by sizes to create a sentence that is a broader cast, but is still semantically in line with the original sentence. And finally, oversampling is simply making copies of the original sentences and adding them to the augmentation population. We used all of these methods in our experiment. I'll get to the data and the specifics of our study in a moment, but now that we have all of these techniques in hand, we have several research questions to answer. Our first question is, does data augmentation improve classification of student answers? For this data set, one important issue will be the balance of the training data between right and wrong answers. Historically, when unbalanced data sets are used to train AI models, the performance is not as high as those that have balanced data sets. So for our first hypothesis, hypothesis 1, it is that using the data set that is both balanced and augmented will improve model performance over just balancing or augmentation alone. Next, we ask if the method used for augmentation affects performance. It is our assumption that our second hypothesis here, that masking will be the most effective due to its alignment with BERT. Lastly, we wonder if the characteristics of the questions and answers affect the model performance, even with data augmentation. We hypothesize that augmentation, where the data set is predominantly wrong answers, will reduce performance over data sets where the answers are mostly correct. Finally, we hypothesize that augmenting from smaller subsets of examples will hurt performance. This is the case where there may be an overwhelming majority of, for instance, correct answers, making the number of incorrect answers in the data so small that augmentation will not lead to much variance in examples. In this case, we believe performance would suffer because the augmentation would consist of a small sampling of possible answers. For this research, Dr. Peter Hastings and myself teamed up with the folks from Vanderbilt University who have performed formative assessments in other research and have a well-defined data set that we can use for analysis. Their project is known as SPICE, Science Projects Integrating Computation and Engineering. It has data from 99 sixth graders on STEM topics. The information was gathered over a 3-week curriculum integrating science, critical thinking, and engineering. The students completed physical experiments on water runoff phenomenon. They used that information to develop science knowledge to build a computational model to simulate water runoff. They then used that information to create a school playground prototype with minimal water runoff, low cost, and high accessibility. This curriculum used evidence-centered design to systematically design formative assessments that track domain-specific knowledge growth over time. Our data sets from this experiment came from the first formative assessment, F1 in this diagram, shown just after Lesson 2. For more information on SPICE, see spiceprojects.org. The picture is used to illustrate rainwater concepts of amount, direction, and absorption. The questions are designed to make the students think about the illustration, understand what the arrow sizes and directions mean, then correct the image to make it accurate. As the questions progress, students are asked more rigorous questions on the path toward understanding the computational model. Each question involves one or more concepts. When assessing the student responses, points are awarded for getting each concept correct. The first question has only arrow size in its concept. The second question has 2 concepts, one for arrow size and one for arrow direction. And finally, the third question is different than the first 2. It evaluates 2 of the 3 possible concepts of absorption, direction, and quantity. The system would have to check for the presence of any of these 3 concepts for that question. Totaling up all of the concepts for all 3 questions gives us 6 possible concepts, which we can use to evaluate the student responses. Therefore, we need to train 6 different BERT models, one for each concept. We analyzed 95 student responses given for each of the 3 questions. 4 of the students did not participate in the task. The responses were hand-graded and coded by the research team into a binary right or wrong grade for each concept. These responses are then fed into a pre-trained BERT model and fine-tuned for binary classification. The student responses from the rainwater runoff lessons gave us some challenges, however. First of all, most of the responses leaned towards either mostly right or mostly wrong answers, creating data imbalance. Data imbalance causes issues during AI model training, and the performance of the model can degrade. Another challenge is that sometimes the majority label is the incorrect answer. When the majority of the answers are correct, those answers tend to be similar to each other and allow the model to correctly identify right answers. Incorrect answers, however, can be anything the student writes, and there's no guarantee that the incorrect responses are similarly related. This can make it difficult for the model to know when it encountered a correct answer. This diagram shows the data from a typical question where the majority class, say quantity of correct answers, are larger than the minority class of incorrect answers. This causes a balance disparity. In the experiment, we chose to have the value of 1x represent the quantity of samples in the majority class. So if the majority class had, say, 76 responses, once the minority class quantity was augmented enough to reach 76 responses, the data set would then be augmented to 1x. We came up with 2 mechanisms for augmenting and balancing the data set. On the left, we increased the minority class in increments of 20% of the balance disparity to go from 0 augmentation to 1x. After experimenting with this method for a while, we noticed that the performance was very inconsistent. So we tried first balancing the data set on the right by reducing the minority set, then augmenting the data in a balanced manner, as shown on the right. Augmentation was added to the data set beyond 1x all the way up to 21x. So for this experiment, we used the student responses for the 3 questions and used that to train 6 unique BERT models on the 6 concepts given in the formative assessment. We selected augmentation levels to see how growing from 0 to 1 would perform, along with growing from 1x to 21x using a Fibonacci series as a multiplier. We divided the data sets so that we used 80% for training and the remaining 20% for testing. And the experiment was performed 10 times, each time using a different random seed on how to break up the training sets and test sets. We used performance measurement of micro F1 and averaged them over all the different augmentation methods. This table summarizes the results from the experiments. You can see from the first column that this shows concepts. The number designates the question that the concept came from, and the lowercase letter indicates the concept being evaluated. So for instance, question 1 had only one concept, C1. Question 2 has 2 concepts, C2A and C2B, and question 3 has 3 concepts. The next column indicates the amount of correct responses and is an indicator of data imbalance. A number higher than 50% indicates that there were more correct answers in the data than incorrect, and the number less than 50% indicates that the majority of the answers were incorrect. The baseline column indicates the performance before augmentation. The a priori performance was calculated by always choosing the majority class in the data set. The unaug data is the model performance prior to augmentation. These values were difficult in some cases, especially those where the majority of incorrect answers were in the data set. The next column shows the maximum performance achieved by averaging the augmented models from all augmentation methods used. The final column shows how much augmentation was needed to achieve the maximum micro F1 score. Recall that research question 1, where we asked if the performance could be improved with data augmentation. The results in this table show that the performance can be improved in most cases. When the data imbalance approaches 89% or more, simply guessing the majority as the classification outperforms our model, regardless of augmentation amount. This supports the first hypothesis that states that both balancing and augmenting data sets improves model performance. However, this is only true if the majority label quantity is less than 89% of the data set. One more note on unbalanced data sets. As you can see in this example, which is concept 2b, the question had mostly incorrect responses, and it was tested in an unbalanced fashion with augmentation alone, and the performance dropped off rapidly, as you can see in the left graph. Once data was balanced, then augmented, the performance was much more stable, as you can see on the right. Therefore, from research question 1, our conclusion is that balancing is imperative, and maintaining that balance throughout the augmentation is essential. These 6 charts show the results from all of the methods of augmentation. Recall that research questions 2 addressed the 4 augmentation methods and speculated as to which was the clear winner. Hypothesis 2 stated that the masking method would be the clear winner since it used BERT as both the AI model and word generator. In these graphs, however, notice that there is little variation in the different methods within each question. There did not appear to be a clear winner among the augmentation methods we used in this experiment. Research question 3 speculated that the characteristics of the question would correlate to performance. So concepts C1, C2A, and C3A were all fact-based, and the others were causal reasoning-based. But the performance does not vary due to the type of question. We did notice, however, that 2 data sets that initially had about 75% majority and 25% minority were questions 2A and 3B, and both achieved very high performance. The others had improvements, but did not appear that one of the questions fared better than the other one. Hypothesis 4, stating that models trained on data sets that had few instances of one class would suffer in performance, was not supported. Some of the techniques used, such as noise or oversampling, either didn't alter the sentences at all or modified them very little. Other techniques replaced words which alter the sentences more. In some cases, if the word replaced is a key word in the sentence, it could possibly alter the sentence meaning. So, augmenting techniques can produce less similar sentences. More aggressive techniques can be employed, and that will be discussed in the future. From our research questions, question 1, discussing balance and augmentation, we noticed that balance does improve performance. Balance is important to achieve first, then augment with equal representation in the model training set, and hypothesis 1, stating that both balance and augmentation would improve model performance, was mostly supported, except for highly imbalanced data sets where simply guessing the majority class would result in higher performance. Question 2 regarded the different types of methods used for augmentation. Not one augmentation technique was a clear winner in our case, so hypothesis 2, which stated that masking would be a clear winner, was not supported by this experiment. And question 3, sentence type, did not seem to predict model performance. From hypothesis 3, which states fact-based concepts would have a different performance than causal reasoning-based concepts, was not supported. Hypothesis 4, which proposed that augmenting from a class with very few examples would hurt performance, but that was not supported either. While we did see the performance level off quickly in our datasets with large percentages of majority classes, we also saw less performance in datasets that started off with nearly equal representation. This clearly needs more research in this area, but augmentation and balancing together seem to improve overall model performance. Adding this method to an evaluation system would reliably give teachers immediate feedback on which students had correct answers and which ones needed a little bit more help. Overall, we saw improvements in the performance of models using balanced and augmented data. There were limits on how much augmentation could be applied before performance either leveled off or degraded, and this seemed to be between 3x and 8x augmentation. For the future direction, we intend to continue this research with more aggressive techniques to experiment to find the right combination of techniques to improve performance. We intend to try back translation and generating sentences from just a few keywords. We also intend to try these techniques on different data sets to see if the model generalizes and if we can see similar improvements. We can also try on public data sets to see if benchmarks can be improved upon. Lastly, we'll further study the categorization of concept types to see if that can be improved for classification.